Hi, this is Mark Weitzman. Welcome back to Quantum Field Theory, a Student's Perspective. In this sequence of videos, I'm going to start Lesson 3 on the canonical quantization of a scalar field. And so this will be like our first sort of quantum field theory proper. We'll be treating free fields here. So, and the methods that we'll be using are for the most part quite standard, because scalar fields are easy to work with. This will be the first video in the sequence. So for references, just about every QFT book treats scalar fields, but some of them use the path integral approach. So I'm just going to list the ones that use a canonical quantization approach. So first we have our go-to book for the course. He has a pretty short chapter on chapter 3 in the book, and I want to expand on it in these lessons. Then there is Peskin and Schroeder. They have a chapter 2 where they basically start their book with scalar fields. And then the book I'm going to follow most in these lectures are Coleman's lectures, and he covers this material in chapters 2, 3, 4, and he covers it in more detail than most books. Then there's Hatfield's book, and he covers this in chapters 2 and 3. There's the classic book by Borkin and Dell. They cover it in chapters 11 and 12. And there's the old book by, not that old, but Ryder on QFT. Many people like this book, and he covers it and a lot more on different other subjects in chapters 2, 3, 4. Okay. Now my outline for this series of lectures, and it may change, but right now my plan is the first one, which is this video. We're going to cover Fock space and Lorentz measure. Then in 2, we're going to cover Coleman's physical approach, I'll call it. And then the third video, I'm going to cover the canonical quantization approach. The fourth part, I'll probably have an example. Maybe I'll do the second quantization, explain what that term means. Second quantization of the Schrödinger equation. The fifth video is going to be a deep dive video on charged scalar field and gauge invariance. And the last videos will be some problems. I'd like to do a problem from Borkin and Gel on a vector massive vector spin 1, just to show you how to crank the canonical quantization, even if you don't know what I'm talking about. And then I'll probably also do problem 3.4 of Czerniecki's book. So that is the outline. And before I get into Fock space, I just want to remind you that we've seen in the last couple of lectures that it is difficult to formulate, if not impossible, a relativistic quantum theory that maintains causality and Lorentz invariance. So I'll just write impossible to have a relativistic quantum theory that maintains causality and Lorentz invariance. I should say for particles. This is like a particle theory. And we showed the difficulty of this in a previous couple of lectures. And so we are led to a field theory. This is a theory with an infinite number of degrees of freedom, and will have its own problems with respect to infinities and divergences. And that's the fun of quantum field theory, making sense of infinities. So, in chapter 3, Czerniecki starts by reviewing the particle relativistic spin 0. Or spinless particles. I shouldn't say relativistic, I should say non-relativistic. And he has there that the energy, or Hamiltonian, is given by p squared over 2m. And then he suggests, as everybody else does, well, let's just go to define this as omega p. A lot of times I'm going to leave off the vectors on the momentum, and you'll just have to use context to know whether I'm talking about a relativistic 4-vector, or most of the time I'll be talking about just a 3-vector in ordinary momentum space. And the Hamiltonian is given by the integral of d3p omega p. I'll use Czerniecki's notation. And he has the usual commutation and anti-commutation relations that you've all seen many times in the harmonic oscillator. Okay, so and then he asked, will this theory be Lorentz covariant or relativistic? And he immediately decides to try another approach. which is the canonical quantization approach. Now, we'll talk about that in the next part of this lecture. But Coleman, in his book, he decides to pursue this more physical approach. And he refers to the canonical quantization procedure when he talks about it, and he covers it in the next chapter. He says it's like a mechanical approach, a turn-to-crank approach for making pasta. And it works, but you don't quite understand exactly why it works, or you don't get the physics out of it. But eventually he too will go to that approach, as he will explain why, and I'll explain why. But for now, let's pursue the physical approach that he does. And for those of you who are computer science majors, or programmers, this contrast is similar to the bottom up approach of programming. Versus the top-down approach. So what we're going to do here is sort of like the bottom-up approach in programming. So I'm going to start. I can't remember exactly how much I've covered with it. Most of you have probably seen it. But let's just talk about Fock space. Very close to a bad word there. So let's review it for free particles. And what we have is, in the Hilbert space, we have kets. Let's talk about our base states. We have kets such as the obvious ones, like single particle. So this represents a state of the universe where there's a single particle with momentum p. Then we might have states which contain like two particles, momentum p1 or momentum p2. Or it's possible to also have, both have the same momentum. So it's like two particles in this state. We're dealing with, I'm going to just deal with bosons here and indistinguishable particles, so the order won't matter. And we can go on. P1, P2, we could have a three-particle state, dot. Now, okay, and the the normalization would be what we would expect. So P1, P2 would be equal to our standard normalization. Again, I'm not always putting vectors on top of these. Basically, everything I'm going to be doing for quite a while is a 3-vector. So we could have that, and we have the Hamiltonian. It's a free particle Hamiltonian, so H acting on a ket P is just equal to, the energy of the particle, which is omega P, acting on P. We could also talk about the momentum operator, and that would give you the momentum acting on P. And again, omega P is forever defined over and over again. P squared plus m squared. If we're working with a theory of like several types of particles where they have different masses, we'll have to keep track of which omega is which. But for right now, we're not doing that. And just in case you want to see, like for a two-particle normalization, it would be this way. It's going to be two terms. And it just works out like this. And then if we apply like a Hamiltonian of the world to a two-particle state, we're going to get just omega P1, omega P2 acting on P1, P2. Now, using this formalism, which is not the formula we're going to use, a general state psi would be equal to like, I neglected to mention, 0 is the no particle. Or another name is the vacuum state. So psi is going to be equal to psi 0 times 0 plus the integral. A general state psi is going to be a superposition of all the base states. And the only condition is that it has to be normalizable. We put the 1 over 2 factorial. This makes it easier to handle because we'll get two terms when we use this normalization. This will cancel it. But that's not... Oops. I don't know what I did now. So in this formalism, this is very clumsy and difficult to do calculations because it requires an infinite number of wave functions. There's a no particle wave function. We have an amplitude for that. A single particle wave function, we have an amplitude. Then two particle wave functions, we have an amplitude. So this is not going to be easy to keep track of everything. And this is just describing one state. So what do we do? Well, there's a very well-known way to get around this. It's called the occupation number representation. Now, I'm not going to be too rigorous about this. Coleman actually does this or works this out in a discrete basis. He basically puts our system in a box so that the momentum are quantized. This of course, bastardizes our Lorentz symmetry and everything, so it's not a good idea to keep it, and then he takes it away at the end. I'm just going to write down the continuum representation, but it helps to think about it in terms of discrete. And I'll just put helps, if you're having trouble visualizing, to think in the context of a discrete lattice momentum space. So, the occupation number representation is simply, I just want to know for every momentum and for every p, and this is a vector, so this is a 3 vector, and it's an infinite number of momentum. I just want to know for a given momentum how many particles have that momentum. So I just want to know like n of p for all p. So if we have a single particle state, let's say with momentum p0, we would basically say n of p0 equal 1 and n of p equals 0 for all p unequal to p0. And in a similar way, we could do like a 2-particle state. Let's say we have 3 particles. Two have momentum P2, let's say, and one has momentum P1. Then we would just say n of P1 equal 1, n of P2 equal 2, and n of P equals 0 for all P not equal to P1 or P2. So it's a very convenient and easy representation. And basically, when we use this representation, it's fairly easy to see. And we're not using a new Hilbert space. We're just rewriting everything in terms of new basis vectors, basically. But it's very easy to see that the Hamiltonian of the universe is going to be the sum over p of omega p n of p if we're using a discrete basis, or we can write that down as the integral d3p of omega p n of p. I'm leaving out 0-point energies for now. And so what this tells us is that we have our Hamiltonian is basically an infinite sum of harmonic oscillator Hamiltonians, one for each point in momentum space. Now, the analogy to the harmonic oscillators is very clear, but it's a little different because the harmonic oscillator, what we have is like excitation level. We have one particle, but we have like an excitation level. Like let's say our particle is in phi 7. That means it's got an energy, E n equal to 7 h bar omega, leaving out again the 0-point energies. When we do the Fock occupation, representation, what we have is 7 particles, each of energy h bar omega, for a total energy of 7 h bar omega. So this sometimes confuses students. I remember when I first studied the harmonic oscillator, or when I first studied quantum field theory, I was a little bit confused. I was saying, wait a minute, with a harmonic oscillator, we have one particle. It just has an energy of 7 h bar omega. Are you saying in quantum field theory that if we have an energy of 7 h bar omega, we don't have a single photon of energy 7 h bar omega, rather we have 7 photons of energy h bar omega? And that's correct. We really do not say that there's one particle of this excitation level. When we have a certain level excited, we say there's like 7 particles of energy h bar omega. So get used to that. And just like for the harmonic oscillator, we define creation and annihilation operators. Here we have the states. So we just define like the, first of all, we'll define like the annihilation operator acting on the vacuum equals 0 for all p. And we'll define like a creation operator, which operates on the vacuum, and that just gives us a state with one particle of momentum p. It creates a particle. So it's the same thing as in the harmonic oscillator, and we have the same commutation relations. Again, this is the continuation. If we were working in a discrete basis, we would have a Kronecker delta here. And this is, again, for all p and p prime. So this is our standard commutations. Again, we have our vacuum. Our Hamiltonian now becomes, very easy to see this, never works when I want to use it. Yeah, these should have vectors on them. Okay. And the total momentum operator, same thing. A dagger P. A P is the number operator. So everything sort of works out as before, and this is just our definition of Fock space. And what we'll do starting in the next video is we will use these operators, these A dagger and A operators, to build fields. So we're taking these particles and we're taking the annihilation and creation operators as fundamental, and we're going to build fields out of them that satisfy certain conditions. And that will lead us to the definition of a scalar field and various properties which we'll work out. For now, I want to, this is a mystery to me, the software, I don't understand it. Why is this frozen? Well, I don't know what to do here. I don't know why it won't scroll. Sorry about this. I haven't used this software in a while. Well, it just opened up a new notebook. I don't want that. All right. Okay, sorry about that. So we'll talk about the scalar field in the next part. Right now I want to talk about relativistic measure. And okay, when dealing with integrals and everything, it's very convenient to have a Lorentz covariant relativistic measure. And Sernecke uses the notation d tilde k. And I'll give you his definition in a second. But imagine we have a function f of k, which is Lorentz invariant. Then, if we have an integral like d tilde k, f of k, we would like to change coordinates and have it equal to the integral of d tilde k prime, f of k prime. So, if d tilde k is equal to d tilde k prime, and f of k equals, call this f prime k, equals f prime k prime, you know, we're okay. I'm not sure I want that to be a different function. I'll have to think about that for a second. But so this is what we're trying to achieve. If we can achieve this, then the other part usually takes care of itself by itself. So Sernecke defines his invariant measure as, it's a pretty standard definition, d3k 2 pi cubed 2 omega. And omega is equal to the square root, as I said, always k squared plus m squared. So I'm using the variable k here. Don't worry about these factors of 2 pi cubed. They're just designed to make everything come out nice in the end. But the way in which this is usually verified, and all quantum field theory books verify it, what they do is they show that basically what we want in four-dimensional space-time, momentum space, let's call this P0, let's call this P. This is the hyperboloid, you know, p squared equal to p0 squared minus p squared equal to m squared. So our particle is always on this sheet here. So it might be around here. And we want to have an invariant measure on this sheet. So how do we do that? Well, we know d4p is Lorentz invariant. How do we know this? Remember that for a Lorentz transformation that's restricted, we're always working with restricted no parity, no time reversal or anything like that. We'll have this. So that tells us that d4p equals d4p prime, where p prime equal lambda p. Now, so we can get a measure that's restricted to this sheet. All we have to do is we multiply d4p by a delta function, p squared minus m squared. Here, when I don't have a vector on it, this is a genuine 4 vector. So I have p squared minus m squared, and then multiply it by theta of p0. This is the step function. Remember, this is the Heaviside step function. Theta of x is equal to 1 if x is greater than or equal to 0. Theta of x at 0, it's not really defined, but x less than 0. Okay, so this guarantees that we have a restricted Lorentz transformation. We're only transforming in the upper sheet, not the lower sheet. And this guarantees that p squared equal m squared, which defines the sheet. So this will be Lorentz invariant. And then we just evaluate it by, we take the integral over dp0 d3p, so that's what d4p is. I have del p squared minus m squared, theta p0. Now this is the integral from minus infinity to infinity, dp0, del. And what is, since, remember, p squared is equal to p0 squared minus p squared. So this whole thing, this whole argument here is just p0 squared minus omega p squared. So I can factor that. I get p0 minus omega p times p0 plus omega p. I have theta of p0. I have d3p. So this is equal to the integral from minus infinity to infinity, dp0. Now, the delta function, when you have a product of delta functions, you should remember that delta, like, let's say ax is equal to 1 over the absolute value of a times x. I'm not going to go through all these properties, but you should be able to see that basically when we're integrating with p0 near omega p, this is basically a constant 2 omega p. This becomes del p0 minus omega p. I can prove these properties to you, but this is something you should know. Plus del p0 plus omega p over 2 omega p times theta p0 d3p. Now, because this requires p0 to be greater than omega p, and omega p is positive, this term is just 0. So we're left with just the integral from minus infinity to infinity dp0 del p0 minus omega p over 2 omega p. Actually, I can even make this 0 over here, and we don't have to worry about theta p0. And this is just going to be equal to d3p over 2 omega p. And in this formula, omega p is, again, always defined by p squared plus m squared, and this is equal to p0. Okay. Now, I'm going to waste some time here, and I'm going to steal a problem from Coleman's book, 1.1 of Coleman. Does the computation with brute force. So I definitely don't recommend this in the sense that you should be comfortable with these delta function manipulations. But if you're not, I'm going to convince you that it is in fact correct anyway. So we want to show that d3p over 2 omega p is equal to d3 p prime 2 omega p prime under a restricted Lorentz transformation. So it's obvious that for rotations this is clear. D3p is obviously rotationally invariant. When we do a rotation, the volume in three-dimensional space doesn't change. And omega p is just given by the magnitude of the momentum vector. When we do a rotation, it's obvious that the magnitude of the momentum vector doesn't change. This definition of a rotation. So we don't have to verify rotations. All we have to do is boost. We have to verify by boost, and by symmetry, it's kind of obvious. We only to verify for one boost, and let's take it in the z direction. So a boost in the z direction, lambda, would be given by, we're working in momentum space again, omega px, py, pz goes to omega prime, px prime, py prime, pz prime, and this is equal to, if you remember your Lorentz transformations, omega hyperbolic cosine chi plus pz hyperbolic sine chi, comma px, comma py, comma pz hyperbolic cosine chi plus omega hyperbolic sine chi. Okay. And chi is the rapidity parameter, and it's given by hyperbolic tan chi is equal to v. Remember, we're using c equal 1. Okay, so under this boost, if we just look at the momentum coordinates, d3p goes to d3p prime which is equal to the Jacobian times d3p. And the three-dimensional Jacobian is equal to, the usual definition of Jacobian. I should write this in case you've ever seen it. So this tells you to take like partial of px prime with respect to px. The next entry is the partial of px prime with respect to py. Partial of px prime with respect to pz. Then I have the partial of py prime with respect to px. Partial of py prime with respect to py, partial of py prime with respect to pz. Finally, I have the partial of pz prime with respect to px. Now, because we're working with a relatively simple transformation, calculating this is not difficult. And I'll leave it to you to verify very simply that this is equal to 1, 0, 0, 0, 1, 0. Partial of omega with respect to px, hyperbolic sine chi. Partial of omega with respect to py, hyperbolic sine chi. And then this entry is the only really complicated one. Hyperbolic cosine chi plus the partial of omega with respect to pz sine chi. Okay, and then when you work out this determinant, which is trivial because we have the 1-1s, it's just hyperbolic cosine chi plus the partial of omega with respect to pz hyperbolic sine chi. And we can easily compute the partial of omega with respect to pz, partial of pz square root px squared plus py squared plus pz squared plus m squared. And this is just equal to pz over omega. So this leaves us with j is equal to hyperbolic cosine chi plus pz over omega hyperbolic sine chi. And that implies that d3p prime over 2 omega prime is equal to hyperbolic cosine chi plus pz over omega hyperbolic sine chi times d3p divided by 2 omega. If you go back to the transformation above, you'll see how omega transforms. Plus pz hyperbolic sine chi, and this is equal to d3p over 2 omega. So that's what we wanted to do. Now finally, the last thing I want to cover, this can confuse some students, is notation. In many books, just about every quantum field theory book I have seems to use a little bit different notation for when they're building up their scalar fields. So the 3-vector notation, which is very common, just uses these are 3 vectors, p and p prime, del 3p minus p prime. And for the states, okay, but this is not covariant. So many books use a relativistic covariant notation, but they might use the same letters, A and A dagger. That's what you have to be careful for. Coleman is the only one I know that actually uses two different notations. He defines alpha dagger P, and this P is a 4 vector, but P0 is constrained by the usual Marshall condition. So alpha dagger P he defines 2 pi to the 3 halves square root of 2 omega P A dagger P. So when you use this, and a lot of books use this definition, but they don't call it alpha. They just keep calling them A and A daggers. That's what Czernicki does. So, and also the state P, this is again a 4 vector. P is equal to, the square root of 2 pi cubed 2 omega P times our usual 3 vector state. And again, the time component is constrained. And then you have the basic equation, the identity equation. And some books use this as 2 pi or 2 pi cubed. They even have differences there. So you just have to be careful. This is equal to integral d3p 2 pi cubed 2 omega P. These are again 4 vectors. So you could see this measure is invariant. And this is clearly invariant. Because, under a Lorentz transformation, it's unitary. So we're going to have like u dagger u equal 1 when we transform the states. So the commutation relations with the alphas you'll see this in Czernicki's book. So all I'm saying here, and the states have similar normalization relations. So the only thing I can advise is to, be very careful. Don't just copy one equation from one book to another. A lot of times you'll see different things here. Sometimes you'll see square roots over here because they're not using these p's, they're using those. So depending on your definitions, you have to write them different ways. But it should be clear from the commutation relations and the normalization of states how things work. In the next video, we'll go on to the physical approach used by Coleman to get to the scalar field. Thank you very much for watching. And again, this is Mark Weitzman of Quantum Field Theory Students Perspective.